Title: Unveiling the Universe's Secrets, the Enigmas of Dark Matter and Dark Energy. Imagine 95% of our universe is hidden from us. What unseen forces shape the cosmos, and why can't we detect them? Welcome to the cosmos as we know it, or at least as we see it. For centuries, scientists have studied stars, planets, and galaxies, piecing together a grand picture of the universe. Today we have the Standard Model of Cosmology, a remarkably successful theory explaining the universe's origin and evolution, the formation of galaxies and stars. This model relies on what we can measure: light, radiation, gravity from visible matter. It describes the atoms that make up us, the Earth, the Sun, and all the stars. But what if this picture is incomplete? What if everything we observe is just the tip of the iceberg? The first cracks in this neat theory appeared in the 1930s. Swiss astronomer Fritz Zwicky, studying the Coma cluster of galaxies, noticed something odd. The galaxies were moving so fast that they should have flown apart if only visible mass was holding them together. He proposed the existence of an invisible substance he called dark matter, providing extra gravity. His ideas were largely ignored for a long time. However, in the 1970s, American astronomer Vera Rubin and her colleagues found even more convincing evidence. They studied the rotation curves of spiral galaxies, how fast stars orbit the galaxy's center at different distances. According to known physics and the visible mass, stars on the outskirts should have been orbiting slower. But Rubin discovered that stars at the edge were rotating just as fast as those closer to the core. This was only possible if galaxies were surrounded by a huge invisible halo of stuff we can't see, but which exerts a powerful gravitational pull. These observations sent shockwaves through the scientific community. They meant that most of the mass in the universe, the overwhelming majority, isn't made of ordinary atoms, the stuff of everything visible. It wasn't just something we hadn't seen, but something fundamentally different from everything we know. Thus arose one of the greatest mysteries in modern physics. What is this invisible stuff that governs the motion of galaxies and shapes the structure of the cosmos? Our visible universe, with all its billions of stars and galaxies, turned out to be just a small part of a much grander and more mysterious reality. Ever wonder what clues led scientists to believe in invisible matter, and what this ghost controlling the galaxies might be? So, we've established the visible universe is just the tip of the iceberg. But how did scientists conclude there was an invisible ghost holding galaxies together? Let's delve into the indirect, yet compelling, evidence. First and most famously is the mystery of galaxy rotation. Imagine a spiral galaxy. If all its mass were concentrated in the visible stars and gas, stars on the outskirts would orbit much slower than those closer to the center. Like planets around the sun, the farther out, the slower they go. But Vera Rubin's observations revealed a different picture. Stars on the edges of galaxies orbit at almost the same speed as the inner ones. This is possible only if galaxies are embedded in a giant, invisible halo of matter, dark matter. Its gravity keeps these fast-moving stars from flying off into intergalactic space. The second strong piece of evidence is gravitational lensing. Einstein predicted that massive objects warp space-time and the light passing by them. It's like a giant cosmic lens. When light from distant galaxies passes by massive clusters, it's distorted, creating arcs or multiple images. By analyzing these distortions, astronomers can weigh the clusters, and the total mass warping the light is significantly greater than the mass of all the visible stars and gas. This excess gravity again points to the presence of vast amounts of invisible dark matter. Another incredibly convincing piece of evidence comes from observing the bullet cluster, the result of two colliding galaxy clusters. During the collision, the ordinary gas matter slowed down and stayed in the center. But dark matter, which barely interacts with itself, simply passed right through, continuing on its way. This resulted in the centers of gravity, where most of the dark matter is, being offset from the centers of ordinary, visible matter. It was like seeing the shadow of dark matter separated from its light part. So dark matter isn't just a theoretical whim, but a necessary explanation for a range of observed phenomena. But what is it made of? We know it's not ordinary baryonic matter. It's not made of protons and neutrons. If it were, we'd see it. The leading hypothesis suggests dark matter consists of WIMPs, weakly interacting massive particles. They have mass, but interact with ordinary matter and light very weakly. They could be passing through the Earth and even our bodies without leaving a trace. Other candidates exist, such as axions. The search for these particles is a major goal of modern physics. So far, they remain elusive, but their influence on the universe is undeniable. This will change how you understand the universe. Its expansion isn't just continuing, it's accelerating, and something truly immense is behind it: dark energy. In the first half of the 20th century, Edwin Hubble made a revolutionary discovery. The universe isn't static, it's expanding. Galaxies are moving away from each other, and the farther a galaxy is, the faster it moves. This has been confirmed by numerous observations. For a long time, it was believed that gravity, acting between all objects in the universe, should gradually slow down this expansion. Imagine throwing an apple upwards. It initially flies quickly, but then slows down under the Earth's gravity. Scientists expected to see something similar on a cosmic scale. However, nature, as it often does, delivered a surprise. In the late 1990s, two independent groups of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were studying distant Type 1a supernovae. These supernovae are special objects. They explode with almost the same maximum brightness, making them ideal standard candles for measuring cosmic distances. Knowing their true brightness and measuring their apparent brightness, one can accurately determine how far away the supernova is. At the same time, the redshift of light from these supernovae was used to determine their recession velocity. The results were astonishing and completely unexpected. Distant supernovae were dimmer than they should have been if the universe was expanding at a decelerating or even constant rate. This meant they were farther away than expected, and their light had been traveling to us for longer. The only logical explanation was that the expansion of the universe isn't slowing down, but is in fact accelerating. It was like throwing an apple up, and instead of slowing down, it suddenly started accelerating away from the Earth. The discovery of the accelerated expansion of the universe was one of the most important and unexpected news in cosmology. It earned the Nobel Prize in Physics in 2011 for the leaders of these research efforts: Saul Perlmutter, Brian Schmidt, and Adam Rees. But what is causing this acceleration? Gravity, as we know, attracts. There must be some unknown force that repels objects from each other. overcoming gravitational attraction. This mysterious force was named dark energy. Unlike dark matter, which is thought to be composed of particles and has mass, dark energy, according to current thinking, is a property of space itself. It's evenly distributed throughout the universe and doesn't get diluted as it expands. This means that as the volume of the universe increases, the amount of dark energy in it grows, increasing the repulsive pressure and accelerating the expansion. Dark energy is something we can't directly observe or measure yet, but its influence on the fate of the universe is colossal. It makes up approximately 68% of the total energy mass of the universe, dominating all other components. Its nature remains one of the greatest mysteries, but its existence is a cornerstone of modern cosmology. Imagine the entire visible universe as a giant cosmic ballet. But who's conducting this grand performance, assembling stars and galaxies into majestic ensembles? And who suddenly changed the tempo, causing the entire stage to expand at an increasing rate? We've already delved into the world of two of the greatest cosmic mysteries: dark matter, the invisible gravitational glue, and dark energy, the mysterious force driving the universe apart. But how does this shadow duo actually shape and determine the fate of everything we see and don't see? Let's start with dark matter. Imagine the universe after the Big Bang. It was almost perfectly uniform, but with microscopic density fluctuations. Ordinary matter, gas, dust, hydrogen, and helium was too hot and under pressure from radiation to quickly start collapsing under its own gravity. But dark matter interacts only gravitationally and isn't affected by the pressure of light. This allowed it to begin clumping into halos, invisible gravitational wells, much earlier than ordinary matter. These halos of dark matter became a kind of skeleton or scaffolding for the universe. As these clumps of dark matter grew, they began to attract ordinary baryonic matter. Gas and dust, cooling down, fell into these gravitational traps, concentrating and becoming denser. It was within these clumps of dark matter that the first stars formed, and then the first galaxies. Thus, dark matter played a crucial role in the formation of the large-scale structure of the universe. Giant clusters of galaxies arranged along filaments, and vast empty spaces called voids. This cosmic web is the result of the gravitational influence of dark matter. Without it, the universe would be much more uniform, and galaxies like ours likely wouldn't have formed. Now, let's turn to dark energy. If dark matter acts as an architect, assembling building materials, then dark energy is the force that constantly expands space itself. On the scales of galaxies, and even clusters of galaxies, the gravity of dark matter and ordinary matter is strong enough to hold them together. That's why our Milky Way galaxy isn't flying apart, and we don't see neighboring stars accelerating away from us. However, on very large scales, between clusters of galaxies, dark energy takes over. Its repulsive effect begins to dominate over the attractive gravity of matter. This is what leads to the observed accelerated expansion of the universe. Galaxy clusters, which once might have merged, or at least slowed down their mutual motion, are now doomed to move away from each other at an ever-increasing rate. This means that the fate of the universe directly depends on the balance of these two invisible forces. If dark energy continues to dominate, the universe will expand faster and faster, becoming colder and more rarefied. Galaxies will move away from each other so quickly that they will eventually become invisible to observers in other galaxies. This is the scenario of the Big Freeze, or heat death, when all heat will dissipate and the universe will plunge into eternal darkness and cold. The interaction of dark matter, which assembles, and dark energy, which pushes apart, defines the very fabric and future of our cosmos. Did you know that billions of invisible dark matter particles are passing through your body right now? And scientists around the world are spending hundreds of millions of dollars trying to catch even one of them in giant underground laboratories and space observatories. The mysteries of dark matter and dark energy continue to captivate scientists around the world. If these invisible components make up 95% of our universe, then discovering and studying them is key to a complete understanding of the cosmos. Today, we stand on the verge of great discoveries, thanks to an entire army of detectors and telescopes, working both on Earth and in space, trying to catch these elusive entities. Let's start with dark matter. The main idea of direct detection is to try to catch those elusive WIMP particles, weakly interacting massive particles, that we assume are passing through us every second. The problem is that they interact with ordinary matter incredibly weakly. To do this, giant underground laboratories are created, deep underground, to protect the detectors from cosmic rays and other interference. Examples of such experiments are Xenon T in Italy and Lux Zeppelin in the USA. They are based on huge tanks filled with ultra-pure liquid xenon. The theory is this: if a WIMP particle collides with the nucleus of a xenon atom, it will cause a tiny flash of light or a pulse of heat, which can be detected by ultra-sensitive sensors. So far, these experiments haven't yielded a definitive direct detection, but they are constantly increasing sensitivity, narrowing down the range of possible properties of dark matter. In addition to the direct search, there is also an indirect one. It aims to detect the products of the decay or annihilation of dark matter particles. If WIMP particles collide with each other, they can annihilate, producing ordinary particles such as gamma rays, positrons, or neutrinos. Space telescopes such as Fermi-LAT, Fermi Gamma Ray Space Telescope, and the AMS-02 spectrometer on the International Space Station are constantly scanning the sky, looking for anomalies in the cosmic ray spectrum that could indicate such events. For example, an excess of positrons at certain energies could be a signal of dark matter, although so far, these signals can be explained by other astrophysical processes. Studying dark energy is a completely different task, since it's a property of space itself. Here, scientists focus on its influence on the expansion of the universe. This is done using large-scale cosmological surveys, which build three-dimensional maps of the distribution of galaxies at vast distances. Projects such as the Dark Energy Survey, DES, the Future Euclid Space Telescope, and the Vera Rubin Observatory, LSST, collect huge amounts of data. They measure distances to thousands of Type 1a supernovae, study baryon acoustic oscillations, BAO, imprints of sound waves in the early universe that are visible in the distribution of galaxies today. By analyzing these data, scientists can accurately determine how the expansion rate of the universe has changed over time, and thus understand the properties of dark energy. Is it a constant cosmological constant, as Einstein suggested? Or does its density change over time? The answer to this question is fundamental to understanding the future of the universe. Imagine, after all our discoveries, we've realized that we only know 5% of the universe. This isn't just a scientific fact. It's a challenge that makes us rethink everything, from our origins to the great destiny of the cosmos. We've come a long way, exploring the invisible forces that conduct the cosmic ballet. From the first hints of missing mass to the stunning discovery of the accelerated expansion of the universe, dark matter and dark energy have changed our understanding of the cosmos forever. The main conclusion we can draw is that everything we see, what we are made of, our planets, stars, and galaxies, is only a negligible 5% of the total content of the universe. The remaining 95% is the mysterious shadow duo. These aren't just scientific facts. They are a revolution in our worldview. For millennia, humanity has tried to understand the universe based on what is available to our senses and instruments. Today, we realize that our knowledge concerns only a small part of reality. This forces us to rethink the fundamental laws of physics. If there are new forms of matter and energy that don't fit into our standard model of elementary particles, then this model is incomplete. We are on the verge of creating a new physics that can explain these phenomena. What prospects are opening up for science? They are truly breathtaking. The search for dark matter continues with doubled force. Each new experiment, whether underground detectors or space observatories, brings us closer to solving its nature. Perhaps we will discover completely new particles that don't interact with our world in the usual way, but whose gravitational influence has shaped the universe since its very inception. This could be a discovery comparable to the discovery of the electron or neutrino. As for dark energy, there are even more mysteries here. Is it a constant, cosmological constant, as Einstein suggested? Or does its density change over time? The answer to this question will determine the ultimate fate of the universe. If dark energy intensifies, we face the Big Rip, when even atoms will be torn apart. If it weakens, perhaps the expansion will slow down or even be replaced by contraction. The Big Crunch. Observations of distant galaxies and supernovae will continue with even greater precision in order to compile a complete history of the expansion of the universe. These studies aren't just an academic interest. They teach us humility before the grandeur of the cosmos and inspire new discoveries. They show that the deepest secrets may be hidden right under our noses, or more precisely, around us. Understanding dark matter and dark energy could lead to completely new technologies, new sources of energy, and even a revision of our place in the universe. We live in an era when fundamental questions about the nature of reality remain unanswered, and this makes science incredibly alive and exciting. The future of cosmology is a future full of uncertainty and perhaps the most grandiose discoveries in human history. We hope this journey into the world of the invisible forces of the universe has inspired you as much as it has us. If you're ready to continue exploring the deepest mysteries of the cosmos and stay up to date on the latest discoveries, subscribe to the Epoch Echoes channel and like this video. Your support helps us unlock new horizons of knowledge. See you soon in the vastness of the universe.